Group 16 elements: oxygen, sulfur, selenium, tellurium, polonium, and livermorium constitute group 16 of the periodic table. This is sometimes known as group of chalcogens. The name is derived from the Greek word for brass and points to the association of sulfur and its congeners with copper. Most copper minerals contain either oxygen or sulfur and frequently the other members of the group. Occurrence: oxygen is the most abundant of all elements on Earth. Oxygen forms about 46.6% by mass of Earth's crust. Dry air contains 20.946% oxygen by volume. However, the abundance of sulfur in Earth's crust is only 0.03 to 0.1%. Combined sulfur exists primarily as sulfates such as gypsum, CaSO4.2H2O, Epsom salt, MEgSO4.7H2O, Bright, BaSO4, and sulfides such as galena, PbS, zinc blende, ZnS, copper pyrite, CuFeS2. Traces of sulfur occur as hydrogen sulfide in volcanoes. Organic materials such as eggs, proteins, garlic onion, mustard, hair, and wool contain sulfur. Selenium and tellurium are also found as metal selenides and tellurides in sulfide ores. Polonium occurs in nature as a decay product of thorium and uranium minerals. Livermorium is a synthetic radioactive element. Its symbol is Lv. Atomic number 116. Atomic mass 292 and electronic configuration Rn 5f14, 6d10, 7s2, 7p4. It has been produced only in very small amount and has very short life, a small fraction of 1 second. This limits the study of properties of Lv. Here, except for livermorium, important atomic and physical properties of other elements of group 16 along with their electronic configuration are given. Some of the atomic, physical, and chemical properties and their trends are discussed below. Atomic number: oxygen 8, atomic mass 16, electronic configuration helium 2s2 2p4, covalent radius 66, ionic radius 140, electron gain enthalpy minus 141, ionization enthalpy 1314, electronegativity 3.5, density 1.32, melting point 55, boiling point 90, oxygen state -2, -1, 1 and 2. Electronic configuration: the elements of group 16 have 6 electrons in the outermost shell and have NH2 and P4 general configuration. Atomic and ionic radii: due to increase in number of shells, atomic and ionic radii increase from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. Ionization enthalpy: ionization enthalpy decreases down the group. It is due to increase in size. However, the elements of this group have lower ionization enthalpy values compared to those of group 15 in the corresponding periods. This is due to the fact that group 15 elements have extra stable half-lived p orbitals electronic configuration. Electron gain enthalpy: because of compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onwards, the value of gain becomes less negative up to polonium. Electronegativity: next to fluorine, oxygen has the highest electronegativity amongst the elements. Within the group, electronegativity decreases with an increase in atomic number. This implies that the metallic character increases from oxygen to molybdenum. Physical properties: some of the physical properties of group 16 elements are given in table. Oxygen and sulfur are nonmetals. Selenium and tellurium metalloids. whereas polonium is a metal. Polonium is radioactive and is short-lived. Half-life 13.8 days. All these elements exhibit allotropy. The melting and boiling points increase with an increase in atomic number down the group. The large difference between the melting and boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule, whereas sulfur exists as polyatomic molecule. Chemical properties, oxidation states and trends in chemical reactivity. The chemical elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, except in the case of OF2 where its oxidation is +2. Other elements of the group exhibit +2, +4, +6 oxidation states, but +4 and +6 are more common. Sulfur, selenium and tellurium usually show +4 oxidation state. In their compounds with oxygen and +6 with fluorine, the stability of +6 oxidation state decreases down the group and stability of +4 oxidation state increases. Bonding in +4 and +6 oxidation state is primarily covalent. Anomalous behavior of oxygen. The anomalous behavior of oxygen, like other members of p block present in second period, is due to its small size and high electronegativity. One typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding in H2O, which is not found in H2S. The absence of d orbitals in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in case of other elements of the group, the valence shell can be expanded and covalence exceed 4. Reactivity with hydrogen. All the elements of group 16 form hydrides of type H2E. Some properties of hydrides are given. Their acidic character increases from H2O to H2TE. The increase in acidic character can be explained in terms of decrease in bond enthalpy for dissociation of He bond down the group. Owing to the decrease in enthalpy for the dissociation of He bond down the group, the thermal stability of hydrides also increases from H2O to H2PO. All the hydrates except water possess reducing property, and this character increases from H2S to H2TE. Reactivity with oxygen. All these elements form oxides of the EO2 and EO3 types, where E is equals to S, Se, Te or PO. Ozone and sulfur dioxide are gases, while selenium dioxide is solid. Reducing property of dioxide decreases from SO2 to TeO2. SO2 is reducing while TeO2 is an oxidizing agent. Besides EO2 type, sulfur, selenium and tellurium also form EO3 type oxides. Both types of oxides are acidic in nature. Reactivity towards halogens. Elements of group 16 form a large number of halides of the type EX6, EX4, EX2, where an element of the group and E is element of the group and X is a halogen. The stability of halides decreases in the order F negative, Cl negative, Br negative, I negative. Amongst hexahalides, hexafluorides are the only stable halides. All the hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride SF6 is exceptionally stable for steric reasons. Among tetrafluorides, SF4 is a gas, SeF4 is a liquid, and TeF4 is a solid. These fluorides have sp3d hybridization and thus have trigonal bipyramidal structures in which one of the equatorial position is occupied by a lone pair of electrons. The geometry is also regarded as seesaw geometry. All elements except oxygen form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides are dimeric in nature. Examples are S2F2, S2Cl2, S2Br2, Ac2Cl2 and Ac2Br2. These dimeric halides undergo disproportion as given below. 2Ac2Cl2 gives AcCl4 plus 3Ac. Dioxygen preparation. Dioxygen can be obtained in the laboratory in the following ways: by heating oxygen containing salts such as chlorate, nitrates and permanganates. 2KClO3 on heating gives 2KCl plus 3O2. By thermal decomposition of the oxides of metal low in electrochemical series and higher oxides of some metals. 2Ag2O gives 4Ag plus O2. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. 2H2O2 gives 2H2O plus O2 on a large scale. It can be prepared from water or air. Electrolysis of water leads to release of hydrogen at the cathode and oxygen at the anode. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapor, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. Properties: dioxygen is a colorless and odorless gas. Its solubility in water is to the extent of 3.08 cm cube in 100 cm cube water at 293 Kelvin, which is sufficient for the vital support of marine and aquatic life. It liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen atom has three stable isotopes, O16, O17 and O18. Molecular oxygen O2 is unique in being paramagnetic in spite of having even number of electrons. Dioxygen directly reacts with nearly all metals and non-metals except some metals and some noble gases. Its combination with other elements is often strongly exothermic, which helps in sustaining the reaction. However, to initiate the reaction, some external heating is required, as bond dissociation enthalpy of oxygen-oxygen double bond is high. Some of the reactions of dioxygen with metals, non-metals and other compounds are given below. 2Ca plus O2 gives 2CaO, 4Al plus 3O2 gives 2Al2O3, P4 plus 5O2 gives P4O10, C plus O2 gives CO2. Some compounds are catalytically oxidized. For example, 2SO2 plus O2 in the presence of V2O5 gives 2SO3, 4HCl plus O2 gives CuCl2, 2Cl2 plus 2H2O. Uses: in addition to its importance in normal respiration and combustion processes, oxygen is used in acetylene welding in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, high altitude flying, and in mountaineering. The combustion fuels, high designs in liquid oxygen, provides tremendous thrust in rockets. Simple oxides: a binary compound of oxygen with another element is called oxide. As already stated, oxygen reacts with most of the elements of the periodic table to form oxides. In many cases, one element forms two or more oxides. The oxides vary widely in their nature and properties. Oxides can be simple or mixed. Simple oxides can be classified on the basis of their acidic, basic or amphoteric character. An oxide that combines with water to give an acid is termed as acidic oxide. For example, SO2 combines with water to give H2SO3, an acid. As a general rule, only non-metal oxides are acidic, but oxides are some metals in high oxidation state have acidic character. The oxide which give a base with water are known as basic oxides. For example, CaO combines with water to give CaOH whole twice a base. In general, metallic oxides are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acids as well as alkalis. For example, Al2O3 reacts with acids as well as alkalis. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Example of neutral oxides are CONO and N2O. Ozone. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in atmosphere at sea level. At a height of about 20 kilometers, it is formed from atmospheric oxygen in the presence of sunlight. This ozone layer protects the Earth's surface from an excessive concentration of ultraviolet radiations. Preparation. When a slow dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone 10% occurs. The product is known as ozonized oxygen. 3O2 gives 2O3. Since the formation of oxozone from oxygen is an endothermic process, it is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. If concentrations of ozone greater than 10% are required, a battery of ozonizers can be used. A pure ozone can be condensed in a vessel surrounded by liquid oxygen. Properties. Pure ozone is a pale blue gas, dark blue liquid, and violet black solid. Ozone has a characteristic smell and in small concentration it is harmless. However, if the concentration rises above about 100 parts per million, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results in the liberation of heat and increase in entropy. These two effects reinforce each other, resulting in large negative Gibbs energy change for its conversion into oxygen. It is not equally surprising, therefore, high concentration of ozone can be dangerously explosive. Due to the ease with which it liberates atoms of nascent oxygen, it acts as a powerful oxidizing agent. For example, it oxidizes lead sulfide to lead sulfate and iodide ions to iodine. When ozone reacts with an excess of potassium iodide solution buffered with a borate buffer, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a qualitative method for estimating O3 gas. Experiments have shown that nitrogen oxides combine very rapidly with ozone, and there is thus the possibility that nitrogen oxides emitted from the exhaust systems of supersonic jet airplanes might be slowly depleting the concentration of the ozone layer in upper atmosphere. Another threat to this ozone layer is probably posed by the use of freons, which are used in aerosol sprays and as refrigerants. The two oxygen-oxygen bond length in the ozone molecule are identical, and the molecule is angular as expected with a bond angle of about 117 degree. It is a resonance hybrid to main forms. It is used as a germicide, disinfectant, and for sterilizing water. It is also used for bleaching coils, ivory, flour, starch, etc. It acts as an oxidizing agent in the manufacture of potassium permanganate. Sulfur. Allotropic forms. Sulfur forms numerous allotropes, of which the yellow rhombic alpha sulfur and monoclinic beta sulfur forms are the most important. The stable form at room temperature is rhombic sulfur, which transforms to monoclinic sulfur when heated above 369 Kelvin. Rhombic sulfur, alpha sulfur. This allotrope is yellow in color, melting point 385.8 Kelvin and specific gravity 2.06. Rhombic sulfur crystals are formed on evaporating the solution on roll sulfur in CS2. It is insoluble in water but dissolves to some extent in benzene. Alcohol and ether. It is readily soluble in CS2. Monoclinic sulfur, beta sulfur. Its melting point is 393 Kelvin and specific gravity 1.98. It is soluble in CS2. This form of sulfur is prepared by melting rhombic sulfur in a dish and cooling till crust is formed. 2 holes are made in the crust and the remaining liquid poured out. On removing the crust, colorless needle-shaped crystals of beta sulfur are formed. It is stable above 369 Kelvin and transforms into alpha sulfur below it. Conversely, alpha sulfur is stable and below 369 Kelvin and transforms into beta sulfur above this. At 369 Kelvin, both the forms are stable. This temperature is called transition temperature. Both rhombic and monoclinic sulfur have acid molecules. These acid molecules are packed to give different crystal structures. The acid ring in both the forms is puckered and has a crown shape. The molecular dimensions are given. Several other modifications of sulfur containing 6 to 20 sulfur atoms per ring have been synthesized into the last 2 decades. In the cyclo S6, the ring adopts the chair form and the molecular dimensions are shown. At elevated temperatures, S2 is dominant species and is paramagnetic like O2. Sulfur dioxide preparation. Sulfur dioxide is formed together with a little 6 to 8% sulfur trioxide when sulfur is burned in air or oxygen. In the laboratory, it is readily generated by treating a sulfide with dilute sulfuric acid. Industrially, it is produced as a byproduct of the roasting of sulfide ores. The gas after drying is liquefied under pressure and stored in steel cylinders. Properties: sulfur dioxide is a colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature under a pressure of 2 atmospheres and boils at 263 Kelvin. Sulfur dioxide, when passed through water, forms a solution of sulfurous acid. SO2 plus H2O gives H2SO3. It reacts readily with sodium hydroxide solution, forming sodium sulfide, then reacts with more sulfur dioxide to form sodium hydrogen sulfide. In its reaction with water and alkalis, the behavior of sulfur dioxide is very similar to that of carbon dioxide. Sulfur dioxide reacts with chlorine in presence of charcoal to give sulfiryl chloride SO2Cl2. It is oxidized to sulfur trioxide by oxygen in the process of vanadium oxide catalyst. SO2 plus Cl2 gives SO2Cl2. 2SO2 plus O2 in presence of V2O5 gives 2SO3. When moist, sulfur dioxide behaves as a reducing agent. For example, it converts iron 3 ions to iron 2 ions and decolorizes acidified potassium permanganate solution. The latter reaction is a convenient test for the gas. 2Fe3 positive plus SO2 plus 2H2O gives 2Fe2 positive plus SO4 2 negative plus 4H positive. 5SO2 plus 2MnO4 negative plus 2H2O gives 5SO4 2 negative plus 4H positive plus 2Mn2 positive. The molecule of H2SO2 is angular. It is a resonance hybrid of the two canonical forms. Sulfur dioxide is used in refining petroleum and sugar, in bleaching wool and silk, and as an anti-chlor, disinfectant and preservative. Sulfuric acid, sodium hydrogen sulfide, and calcium hydrogen sulfide are manufactured from sulfur dioxide. Liquid SO2 is used as a solvent to dissolve a number of organic and inorganic chemicals. Oxoacids of sulfur. Sulfur forms a number of oxoacids such as H2SO3, H2S2O3, H2S2O4, H2S2O5, H2SX06, X225, H2SO4, H2S2O7, H2SO5, H2SO8. Some of these acids are unstable and cannot be isolated. They are known in aqueous solution or in the form of their salts. Structures of some important oxoacids are shown. Sulfuric acid manufacture. Sulfuric acid is one of the most important industrial chemicals worldwide. Sulfuric acid is manufactured by contact process, which involves three steps: burning of sulfur or sulfide ores in air to generate SO2, conversion of SO2 to SO3 by reaction with oxygen in the presence of a catalyst, and absorption of SO3 in H2SO4 to give oleum. A flow diagram for the manufacture of sulfuric acid is shown. The SO2 produced is purified by removing dust and other impurities such as arsenic compounds. The key step in the manufacture of H2SO4 is the catalytic oxidation of SO2 with O2 to give SO3 in the presence of V2O5. The reaction is exothermic, reversible, and the forward reaction leads to a decrease in volume. Therefore, low temperature and high pressure are the favorable conditions for maximum yield. But the temperature should not be very low, otherwise rate of reaction will become slow. In practice, the plant is operated at a pressure of 2 bar and a temperature of 720 Kelvin. The SO3 gas from the catalytic converter is absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of the desired concentration. In the industry, two steps are carried out simultaneously to make the process a continuous one and also to reduce the cost. SO3 plus H2SO4 gives H2S2O7. The sulfuric acid obtained by contact process is 96 to 98% pure. Properties: sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 Kelvin. The acid freezes at 283 Kelvin and boils at 611 Kelvin. It dissolves in water with evolution of a large quantity of heat. Hence, care must be taken while preparing sulfuric acid solution from concentrated sulfuric acid. The concentrated acid must be added slowly into water with constant stirring. The chemical reactions of sulfuric acid are as a result of following characteristics: low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. In aqueous solution, sulfuric acid ionizes in two steps. H2SO4 plus H2O gives H3O positive plus HSO4 negative. HSO4 negative plus H2O gives H3O positive plus SO4 2 negative. The larger value of Ka means that H2SO4 is largely dissociated into H positive and HSO4 negative. Greater the value of dissociation constant, the stronger is the acid. The acid forms two series of salts, normal sulfates and acid sulfates. Sulfuric acid, because of its low volatility, can be used to manufacture more volatile acids and their corresponding salts. Concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing them through sulfuric acid, provided that the gases do not react with the acid. Sulfuric acid removes water from organic compounds It is evident by its jarring action on carbohydrates. Hot concentrated sulfuric acid is moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acids. Both metals and nonmetals are oxidized by concentrated sulfuric acid, which is reduced to SO2. S plus 2H2SO4 gives 3SO2 plus 2H2O. Sulfuric acid is very important industrial chemical. A nation's industrial strength can be judged by the quantity of sulfuric acid it produces and consumes. It is needed for the manufacture of hundreds of other compounds and also in many industrial processes. The bulk of sulfuric acid produced is used in the manufacture of fertilizers. Other uses are in petroleum refining, manufacture of pigments, paints and dye stuff, intermediates, detergent industry, metallurgical applications, cleansing metals before enameling, electroplating and galvanizing, storage batteries, in the manufacture of nitrocellulose products, and as a laboratory agent.